Hello everyone, welcome to lecture 58 in the course Diffusion in Solids. So, in the last video we started talking about the diffusion in ionic solids where we covered the point defects and we also talked about diffusion in silver halides. Today we will be taking the example of alkali halides and talk about the features of diffusion in these materials. So, we know the classic example of alkali halide is NaCl. So, in the case of alkali halides, the diffusion mainly occurs by the exchange jump of ions with the vacancies which are the with the vacancies, and here the alkali ions move by the cation vacancies and the halide ions move by the anion vacancies. So, the concentration or the diffusion coefficient for the cations, so dC star can be written as Fv into A square into Cvc into omega Vc. So, this is the tracer self diffusion coefficient of cations, and the dA star can be written as Fv into A square into Cva into omega Va, which is tracer self diffusion coefficient of anions. So, Fv is the correlation factor for the vacancy mechanism. A is the lattice parameter. Omega Vc and omega Va are the corresponding jump frequency, which can be written as for example, omega Vc can be written as nu Vc naught exponential minus Gm Vc by kBt, and the G further can be split as entropy and the enthalpy terms. Similarly, the omega Va can also be written. Now, it is also interesting to see what happens as the diffusivity we plot versus 1 by T. Now, what you see here, so this is a schematic plot. In the last lecture, we will give you some references for this where you can see the data in the actual systems as well. So, in the plot, if you see, then what you see is an region marked as intrinsic and a region marked as extrinsic, and the slope of both of them are different. So, the extrinsic diffusivities are higher than the intrinsic diffusivities, and here as the concentration of the Ci means the concentration of the impurity, as it increases, then what happens, there is the change in the, there is an increase in the diffusivity as well. So, here two terms can be plotted, the d sigma, which is the charge diffusivity, and the tracer diffusivity of anions or the cations in the alkali halides. So, when we are in the intrinsic region, the concentration of the cation vacancy is equal to the Cvc 0, that means this is for the intrinsic region, and similarly this is also equal to Cva 0, which is equal to Cva. So, essentially the cations and anion contributions or concentrations are equal, and therefore, one can write dC star is equal to Fv A square nu C naught exponential. So, here we are combining these two terms. Remember, in the case of silver halides, it was the Frankel product we talked about. So, the Frankel defect exists together. So, here in the case of silver halide, so you had for example, the Ag plus interstitials and the vacancy, the cation vacancy, whereas here you have both the cation vacancy and the anion vacancy, which is the feature of a Schottky defect. So, these here in the alkali halides, Schottky defect is the more dominant one, and therefore, you see that the cation and anion vacancies both contribute to the diffusion. So, when we write dC star, here there are two terms, one is S Sp by 2 plus S Vcm. So, this is the entropy of migration for the cation vacancy, whereas this is the entropy of formation for the Schottky product. So, the by 2 comes because of that. So, here again HSP by 2 plus HVCm. So, this is the migration of the cation vacancy, this is the formation enthalpy for the Schottky pair HSP. Similarly, you can write the expression for anion vacancies. So, remember in the case when you write it for anion vacancy, this does not change because the correlation factor for vacancy remains the same for the given structure. Then A square nu A naught exponential here, this is the migration entropy for the anion vacancy, and here this is a migration enthalpy for the anion vacancy as well. Now, if for the moment we ignore the vacancy pair corrections, then the delta Hc, that is the activation enthalpy of diffusion for the cations, can be written as HSP by 2 plus HVCm. That means Schottky product plus the migration barrier. Then you can also have delta HA is equal to HSP by 2 plus HVAm. Now, in the alkali halide crystals, usually cation vacancies are more mobile than the anion vacancy. You have omega Vc greater than omega Va. This primarily comes because of the different sizes of anions. So, different sizes of anions, Na plus is much smaller than the Cl minus, and therefore, the diffusivity is also of the cations is higher than the anions, although the difference is not so large. In the extrinsic region, if you have added a divalent cation dopant like Ca2 plus, then the concentration of the vacancy is almost nearly equal to the concentration of the impurity. So, the CVC becomes Ci. So, therefore, now the diffusion coefficient of cation can be written as dC star is equal to Fv into A square into Ci into omega Vc, and again omega Vc can be written expanded as this. So, now this whole term Fv A square Ci Vc naught exponential S Vc m by Kb, this is called as d naught C prime. What d naught C prime means is, it is the d naught for the cations when an extrinsic impurity or a dopant is present. So, in the extrinsic region, what is the d naught? And similarly, if you see the previous slide, here this is the d naught C, which is the d naught in the intrinsic region, and we can see here because you are multiplying by this product by this factor Ci, you can see that the d naught values are decreasing. The above equation, this equation assumes that the cation vacancies are not associated with impurity. So, we are neglecting the complex formation, which is not reasonable at very low temperatures. So, this is fine at higher temperatures, the vacancy and the impurity can be far apart, but when it comes to the lower temperatures, then formation of complex is more probable. So, as I indicated that the pre-exponential factor in the case of extrinsic region is less than the pre-exponential factor in the intrinsic region. So, this is proportional to Ci. So, to maintain the Schottky product, cation anion vacancy concentration Cva is decreased. So, because you can see why it comes, because when you are adding, let us say, a divalent cation, then you have to create cation vacancies. So, cation vacancies carry negative charge. So, now these are more. So, therefore, the anion vacancy which carry positive charge has to come down. So, then vacancy pair. So, these equations that we see, there are deviations in this equation that comes because of the existence of the vacancy pair. So, remember vacancy pair are neutral because they are cation and anion vacancy together. So, they are neutral, and therefore, they do not contribute to the ionic conductivity, but they do contribute to the self diffusion. So, we can write dC star total is equal to dC star plus dCp star, where similarly dA star total can be written as dA star plus dAp star. So, these two are the contribution coming from the vacancy pairs. The interactions between cation and the anion vacancy, they become appreciable at the higher temperature. So, these interactions are more prominent at higher temperature. Vacancy pair formation in equilibrium is relevant particularly at the higher temperatures. So, for the complex for the vacancy pair, the D star Cp is written as 2a square Fcp omega Cp into the concentration of the pair. Similarly, here also it is written as 2a square FAP omega Ap into the concentration of the pair. So, we can further write dCp star as 2a square Fcp nu naught C Zp into exponential. Now, here you see that you have GSP minus delta Gp plus Gm Cp. So, the migration terms, formation terms exist, and this is the anion pair diffusivity, very similar looking expression, except whatever here was for cation pair, it becomes anion pair. In the ionic solids at elevated temperatures, so the conductivity is through the motion of ions. So, the motion of ions is what is responsible for the conduction in this ionic solids. So, the total ionic DC conductivity of an alkali halide crystal is written as sigma dC equal to sigma C plus sigma A, which is the partial conductivity of anion and the cation. So, therefore, you can write partial charge diffusion coefficients, which is d sigma C equal to kBt into sigma C divided by Nc into q square, where Nc is the number density of the cations. Similarly, you can write d sigma A is equal to kBt times sigma A divided by Na into q square. For the alkali halides, here the number of cations and the number of anions, the number densities are equal, and it can be written as an ion, that is number of ions. So, therefore, the total charge diffusion coefficient can be written as d sigma is equal to d sigma C plus d sigma A, which is equal to kBt sigma dC by n ion into q square. One very important point, remember that this d sigma, which is the charge diffusivity, it only has the units of diffusion coefficient, but strictly speaking, it is not it does not correspond to any diffusion coefficient. That means it is not really a diffusion coefficient that can be measured by classical Fick's laws. So, by the standard solution of the Fick's law, you cannot measure something like a d sigma. Okay. So, it although the dimension is of diffusivity, but strictly speaking, it is not really a diffusion coefficient. When you are in the extrinsic region, the number of vacancies is dominated by impurity level and approaches doping concentration. The Haven's ratio, we know that it is a ratio of dC star total divided by d sigma C. HRA for the anions is dA star total by d sigma A. If the tracer diffusion and ionic diffusion, they occur by isolated cation and anion vacancies, then both Haven's ratio are equal to the correlation factor of the vacancy diffusion. That means, remember again that in the alkali halides, the Schottky defect is the prominent one. So, you have cation vacancies, you have anion vacancies. If they are isolated, not interacting with each other, not forming a pair, then in that case the Haven's ratio are equal and are equal to the correlation factor of the vacancy diffusion, which is 0.781. And in that case, the dCA plus dA, so the dC star plus dA star is equal to Fv into d sigma C plus d sigma A, where that is equal to Fv into d sigma, Fv into Kb into T sigma dC by C ion whole q square. So, here this equation neglects the effect of the vacancy pair. That is why we said isolated cation and anion vacancies. So, again like previously mentioned that vacancy pairs are neutral, they do not contribute to the ionic conductivity, but they do contribute to the diffusion of both the ionic species. Now, if we try to plot for NaCl, let us say if we take an example of the alkali halide, which is one of the most studied alkali halide, is NaCl. So, in the NaCl, if you try to plot the conductivity versus 1 by temperature, then you again get two regions, one is intrinsic, one is extrinsic. So, in the intrinsic region, the delta H Na plus is equal to HSP by 2 plus HV Na that is the migration enthalpy, and this is the Schottky pair. And extrinsic, the slope reflects the migration enthalpy of the vacancies. There are certain deviations at lower temperatures which are indicated here. These are due to the complex formation between Sr2 plus ions and the cation vacancies. So, the impurity vacancy complexes form. Then the large activation enthalpy at the lower temperatures. So, at the lower temperatures, the large activation enthalpy. So, lower temperatures, the large activation enthalpy is here. So, if you see that these are the temperatures, these are the temperatures where the activation enthalpy is larger. So, we are not talking about this region, we are talking about this deviation, if you can notice a little bit, where the slope is becoming slightly larger. So, the larger activation enthalpy comes because the additional energy now is required to dissociate the vacancy impurity pair. So, you see that the extrinsic here, so this is the intrinsic region where the slope is the maximum. So, here you have two contribution, which is the Schottky pair and also the vacancy. Let us say in the we are talking about the sodium. So, the sodium vacancy, the migration enthalpy term is coming here. Now, as you move to the extrinsic region, the slope changes. That means, in this case the conductivity is changing and the correspondingly conductivity and diffusivities are also related. So, here this is changing because of the addition of the impurities. Now, at the lower temperatures, in the extrinsic region, when you go to the lower temperatures, then the activation enthalpy is becoming slightly larger because of the additional energy that is required to dissociate the vacancy impurity pair. So, I hope it is clear. There is if you try to sum total the sodium and chlorine diffusivity, it is greater than Fv into d sigma, that is the correlation factor multiplied by the charge diffusivity, and this basically comes from the inequality, stems from the fact that the vacancy pair contributes also to the tracer diffusion. In fact, near melting point, about 40% contribution to any tracer diffusion comes from the vacancy pair. So, you can see that as you go further higher and higher, this kind of contribution can increase. The contribution of vacancy pairs to anion tracer diffusion is smaller than that of cation tracer diffusion due to the correlation effects. Now, when we talked earlier, we also saw that isotope effect in some systems people try to measure. So, NaCl is one of such systems. So, isotopes of 22Na and 24Na were used to measure the diffusivities in the single crystal in this temperature range 589 to 796 degree centigrade. And the isotope effect parameter E decreases with increasing temperature from 0.7 to 0.49, suggesting two diffusion mechanisms. In fact, for the diffusion via isolated cation vacancy, EC is equal to Fv into delta Kv, where Fv is equal to 0.781, and Kv is the delta Kv rather is the kinetic energy factor for cation vacancy jumps. Similarly, you can write the expression for anion vacancies also. So, the correlation factor for the vacancy pair mechanism is smaller, hence ECP is less than EC, and an effective isotope parameter can be written as EC into DC star by DC star plus DCP star. Similarly, ECP into DCP star divided by DC star into DC star plus DCP star. Now, coming to the impurity diffusion coefficient, like we have written before. So, impurity diffusion coefficient in the FCC sublattice can be written as d2 is equal to a square omega 2 f2 CVC exponential minus not minus exponential delta G IVC by kBT, where this delta G represents the Gibbs energy of impurity vacancy association, F2 is the correlation factor, omega 2 is the jump rate for the impurity vacancy exchanges. F2, we have seen that this comes from the 5 frequency model that was suggested. So, the similar expression can be written here, omega 1 plus 7 omega 3 F3. You can refer to that lecture where we talked about the 5 frequency models and so on. And if the binding between the vacancy and impurity is tight, then the diffusion dissociation jump rate of the complex omega 3 is negligible, and if you neglect omega 3, you end up F2 is approximately equal to omega 1 divided by omega 1 plus omega 2. If we try to plot the impurity diffusion as a function of the concentration of the divalent impurities, here this also depends upon the nature of the impurity. Either you can have a homovalent impurity. So, I mean here this graph is only for divalent, but what I am trying to say is that when we consider the impurity diffusion, there are two types of impurities that are possible. One is the homovalent impurities. In the homovalent impurities, the vacancy impurity association is due to the size and the polarizability effects, and the activation enthalpies are very similar to those of the self-diffusivities of Na or Cl. Whereas, when you consider the heterovalent diffusivities, the vacancy impurity association has a strong Coulombic attraction to the binding enthalpy. So, when the charge of the heterovalent, when the charge of the material or the dopant that you have added is different, that is known as the heterovalent impurity. Such cases, the vacancy impurity association, it has a strong Coulombic attraction. So, this strong variation of D that you see here at the lower temperatures is because impurity can diffuse only when a vacancy is on a nearest neighbor site. If it is not on a nearest neighbor site, the atomic jumps will not happen and the diffusion will not take place. So, the D2 can be written as 8 by 3 omega A square into omega 2 into F2 into P by 1 plus P. So, if you recall, the P is equal to nothing but the degree of association CIVC divided by Ci. So, you can see here that X is equal to delta G IVC by KBT, and the X1, X2, X3, this is the order in which they are decreasing. If in this equation P is equal to 1, then it is easy to see that the D2 is equal to 8 by 3 A square omega 2 into F2. So, here if P is equal to 1. So, this is the equation if P is equal to 1. Now, remember that if the case is where P is less than 1, so that means here if the P is coming, remember P is nothing but CIVC divided by Ci. So, what it means is that the diffusivity itself is a function of concentration, and if you recollect that the moment the diffusivity depends on the concentration, you cannot take it out of the derivative in the fixed second law, and therefore, the standard solution of fixed second law are not applicable here. So, in the case of interdiffusion, we saw that we are not, because the diffusivity is concentration dependent, you cannot take out that term from the derivative, and therefore, the solutions are more complicated. We will end with few remarks about the alkali halides. Some of them we already mentioned, like predominant intrinsic defects are the Schottky defects, and the formation enthalpy of these defects is between 2 to 2.3 electron volt. And the doping with heterovalent cations or anions is compensated by the formation of the respective cation or the anion vacancies to maintain charge neutrality. The cation vacancy in alkali halides is slightly more mobile and therefore has a greater contribution to the ionic conduction that comes primarily because of the size difference. The ionic conductivity of an alkali halide is both a function of temperature as well as the impurity concentration. In the intrinsic region, equal number of thermal cation and anion vacancies contribute to the conductivity when it is intrinsic region. When you dope these alkali halides with heterovalent cations or anions, the extrinsic conductivity is dominated by the motion of either cation or the anion vacancy, depending on what type of dopant we have added. then it is possible that the complexes between the heterovalent impurities and the vacancies become significant, particularly at the lower temperatures. Why at lower temperatures? Because at higher temperatures they may want to move freely, whereas when at their lower temperatures the movement is restricted, so they have more propensity to form these complexes than at the higher temperatures. The self diffusion in these alkali halides is predominantly mediated by the vacancies. The additional contribution can also come from the neutral vacancy pairs. The extent of this contribution can vary from one alkali halide to other alkali halide. We already indicated that the cationic self diffusion is slightly faster. So, in fact, if you see near the melting temperature, earlier we also derived equations where we neglected the vacancy pair contribution. However, the vacancy pair becomes more predominant when you are at higher temperatures. Near the melting temperatures, it contributes as much as half to the tracer diffusivity. The vacancy pair contribution decreases with decreasing temperature. Actually, this is a nice takeaway question for you. If you see here, although I have not mentioned this time the takeaway separately, but you can remember that when you are talking about the vacancy pair contribution actually is more at a higher temperature than at the lower temperature. Whereas when you talk about, like we talked here about the complexes between the heterovalent impurities and the vacancies, they are more significant at lower temperatures. So, think about it, why there is a difference in this behavior, where the vacancy pair have the contribution more at higher temperatures, whereas the impurity vacancy complex have a higher contribution at lower temperatures. So, the diffusion of the homovalent impurities is similar to self diffusion in the same sublattice, while the diffusion of heterovalent impurities is strongly concentration dependent. And the binding enthalpy between the divalent cation impurities and cation vacancies is approximately 0.5 eV. So, with this we will end the discussion on diffusion in ionic solids. Thank you.